So we did an individual resistor, an individual capacitor, and an individual inductor for our AC circuits. Now we're going to do all three. So this is a series RLC circuit. Now if you go back to those previous videos, remember how we created those capacitive reactance, inductive reactance terms. The reason we did that is because we want to treat them similar to a resistor, because we know that voltage is equal to current times resistance from Ohm's law, and we want to use a similar thing even though we're dealing with capacitors and inductors. So for the RLC circuit, we're going to define the current as equal to the voltage of our AC current divided by this new term Z. Okay, so now notice this kind of looks like V is equal to I times R. It looks like Ohm's law, but it's not exactly, because we've got this Z term down here. This E up here is our EMF that's standing in for the voltage of the AC circuit. This new term Z is defined as the impedance. Impedance is equal to the square root of R squared plus, remember those reactive terms, those reactance terms, chi L minus chi C, let me make sure I have the order on that right, chi L minus chi C, the quantity squared, okay? So this is our impedance term, impedance. Z is equal to the square root of R squared plus chi L minus chi C, the quantity squared. Now, the way I think about this is, if we didn't have the inductor or the capacitor, here I would have that the impedance is equal to the square root of R squared, which would just be R. So then this would immediately go to Ohm's law. It would be I is equal to voltage divided by R. So it turns into Ohm's law if we don't have an inductor or a capacitor. Okay? So this is our impedance term. This now means that the current amplitude, I, is equal to E, the voltage, divided by this term right here, this R squared plus chi L minus chi C, the quantity squared. We're going to replace these two terms with the 1 over omega dL and omega dL for the inductor and 1 over omega dC for the capacitor. So now this is going to be R squared plus omega dL minus 1 over omega dC, and this quantity is still squared. So all I did here was replace the inductive reactance and capacitive reactance with omega dL and minus 1 over omega dC. Okay? Finally, we have a new phase constant that we're going to find. And again, I'm not asking you guys to define this stuff. I'm giving it to you right now. The tangent of the new phase constant for this RLC circuit is equal to chi L minus chi C. We'll make that a little bit more clear. Chi L minus chi C all over R. So this is going to give us the phase constant for this LRC circuit. Okay? Now, make sure you have this in your notes. Now we're going to talk about some special conditions on these things. Okay? Make sure that's in your notes. Okay? Now, some special conditions. This is basically determined by the strength of the inductor, the strength of the capacitor, and the resistor. So these are special conditions. If chi L is greater than chi C, then we say that this is more inductive than capacitive. More inductive than capacitive. More inductive than capacitive. That leads to a positive phase constant. So we have a positive phase constant if chi L is greater than chi C. Okay? If chi C is greater than chi L, so if the capacitive reactance is more than the inductive reactance, then we're going to say that this is more capacitive than inductive. More capacitive than inductive, and this is going to be a negative phase constant. So positive phase constant if chi L is greater, negative phase constant if chi C is greater. Okay? Now, we have the special case. if chi C is equal to chi L, so if the two reactances are equal to each other, this is known as resonance. Resonance. And this leads to phi equal to 0. So the phase constant is going to be equal to 0. If we have resonance, then what that means, since they're both equal to each other, that means that omega d L is equal to 1 over omega d C. Okay, so I'm setting those two guys equal to each other, omega C down here, chi C down here, chi L, omega d times L. And so that means that our resonance frequency is 1 over the square root of LC. So this is your resonance frequency right here, the special case when chi L is equal to chi C. Okay? Again, don't stress too much about this. This is mostly a plug and chug chapter. I'm not going to ask you guys to derive any of this stuff. It's best to just know how to go about doing it.